Hi everyone, today I'm going to discuss a mathematical model to interrogate and characterize emulsion stability via diffusing wave spectroscopy. Emulsions are thermodynamically unstable. An emulsion is destined to phase separate, it is just a question of when. Diffusing wave spectroscopy, or DWS, is a way to non-invasively interrogate changes in size with time in a dense suspension. DWS allows one to observe the evolution of drops and understand the kinetics of emulsion destabilization. In my graduate research, I use an ALV-CGS3 compact goniometer to analyze emulsion samples. Specifically, I work with water and oil emulsions containing engine oil treated with various surfactants to optimize engine oil formulations for specific applications. The ALV instrument is capable of dynamic light scattering, or DLS. However, when the mathematical model I am going to discuss today is applied, it is capable of DWS. DWS allows one to non-invasively probe microreology of emulsion dynamics during structural evolution. For the project I've been working on, it allows me to understand the mechanisms of surfactant composition on emulsion stability. As you can see in the top figure in the bottom panel, an emulsion sample gets analyzed via DWS and you get intensity and an autocorrelation function. From the autocorrelation function, the mean square displacement of droplets can be calculated, which will provide valuable information on emulsion stability and rheology. So I'm going to try to quickly go over how DWS works. So basically they're scattering objects that are suspended in a solution. They have some size and they undergo some motion. The dispersed phase is moving inside of the continuous phase. Light is entering and colliding with the dispersed phase, which changes the trajectory of light. The light that's exiting is out of phase with the light that enters. If you were to focus a detector on the transmitted light, the intensity of transmitted light is going to fluctuate. This is because light coming in is undergoing scattering events, so different amount of light gets through at different times. This is known as intensity fluctuations. So the ALV instrument will output intensity plots as a function of time, as well as a temporal autocorrelation function, G2. Using the secret relation, which I will discuss further, I can obtain G1, the field autocorrelation function. Watching how the autocorrelation function changes in time, I can see how mean size changes in time. At later times, the curve will shift right because bigger particles move slowly and are correlated for a longer time. Displacement is bigger for larger particles. If you know how fast particles are moving and their displacement, you can know their size. And you know if their size stays the same, then typically this means that your emulsion is stable. So to start our mathematical model, we are going to think of light scattering as the oscillation of charged particles. You can see Newton's law written out where you can see the electric field magnitude, and then the solution with electric field oscillating at frequency omega is given by E of t here, and after a momentum balance I'm not going to get into, we get this bottom expression for our electric field for DWS. So as I've mentioned before, intensity fluctuations in time are characterized by their temporal autocorrelation function, G2, which you get from the ELV instrument. Now using the secret relation, we can get G1, our field autocorrelation function. So the secret relation relates intensity, a measurable quantity, to the electric field, a practically immeasurable quantity, so we can extract useful physical information. For a photon traveling through multiple scattering media, the total path length is given by this top expression for S, where Ri is the position of particle I, R0 is the position of the laser, and R sub I plus 1 is the position of the detector, and K sub I is the wave vector. Photon scattering is assumed to be elastic, therefore K sub I is equal to K0, the incident wave vector, which is equal to 2 pi over lambda, where lambda is the wavelength of the laser. The total phase shift, phi of t for a photon, given by the bottom expression here, which is K0 multiplied by the path length. And then we have our electric field, which we've already defined, which is summed over paths P, and where EP is the amplitude of the field from path P at the detector. Using these relationships we just discussed, the autocorrelation function for DWS G1 can be written as the top expression here. P of S is the path length distribution, delta R squared is the mean squared displacement, or MSD, and L star is the transport mean free path. 3 assumptions were applied to arrive at this expression: no interactions between particles, Gaussian distribution, and a large number of scattering events. the continuum limit is applied, which basically is the limit of infinite particles, or as n, therefore s, goes to infinity. The continuum limit applies us to convert the summation in the top expression to an integral in the bottom expression. From this expression for G1, what we want is MSD, which is shown as delta r squared of t. MSD can be modeled to extract the radius of droplets. As you can see, for simple diffusion, MSD is equal to 6dt, where d is the diffusion coefficient. And as we know, radius is found in the expression for d, as shown here. Therefore, radius can quite simply be extracted in the case of simple diffusion. So far, we have an expression for G1, but we need to determine L star before determining MSD. For this model, to get values of MSD, L star was calibrated versus concentration for particles of known size. To get L star, the path length distribution P of S and path length S must be known. Making assumptions about photon motion allows simulations to be run. If enough photons are simulated, accurate P of S and S data can be determined. The three key assumptions for this simulation is a photon acts as a particle undergoing Brownian motion, the photon travels in a straight line of distance L star before its direction is randomized, and when a photon exits the programmed geometry, its angular position relative to the origin determines its angle of detection, not its angle of trajectory. So P of S data is necessary to determine L star, however L star is an input in the simulation to obtain the P of S data. This would require a simulation for every possible L star to be able to analyze experimental samples. Obviously, this is unrealistic, so the solution we have come to is scaling P of S by the average path length. Due to this scaling, P of S data of any arbitrary L star can be used for a single angle of detection. This allows for L star to be an adjustable parameter for curve fitting. With P of S and S data, G1 of T experimental data can now be fit by adjustable parameter L star. Using polystyrene particles with known size, simulations can be assessed for accuracy and scaling. A master calibration curve can now be constructed for all experimental samples. Beer's law, which is seen here, is used to obtain L, the scattering mean free path, and me theory can be used to obtain L star. The calibration curve is shown on the right. The red data point is one of my emulsion samples, and as you can see, L star can be extracted from this calibration curve, and it is in agreement with theory. Now that we have L star, we can calculate MSD. The expression for MSD contains A, the droplet radius, but you need a proper model to extract values of A. As you can see, if your sample exhibits Brownian motion, MSD equals 6dt, and getting A is quite simple. The Python code I used to fit my experimental data uses this Brownian motion model to obtain a value of A. If your sample exhibits ballistic drift motion or sub-Brownian motion, getting A becomes a bit more challenging. If you can get size, you can understand the kinetics of emulsion destabilization. The rate of emulsion destabilization, which can be written as dA dt, is a function of size, 1 over L star, which is proportional to the concentration of droplets per unit volume, and time. For my graduate research, this allows me to write a rate of emulsion destabilization for each concentration of each surfactant that I test. A model for MSD can be chosen by scaling MSD by time. As you can see, if you do this, you will get a slope of 0 for Brownian motion, a negative slope for sub-Brownian motion, and a positive slope for ballistic drift motion. From this information, you can apply the appropriate model to accurately extract radius from MSD. Since the Python code I use to analyze my samples uses Brownian motion, I can only use the value of A at outputs if the scaled MSD curve has a slope of 0. The bottom panel shows a very simple emulsion with half CMC SDS and 20 volume% silicone oil. The MSD curves at different angles are shown in the bottom plots. As you can see from the scaled MSD plots, the sample is showing Brownian motion at time 30, 60, and 90 minutes. Therefore, radius can be accurately reported and rate of destabilization can be calculated for those time points only. The Python code I use to carry out these calculations must be run on a supercomputer in Biotech 8, so unfortunately I cannot run it for you now, but here are some snippets of the code I use to carry out the secret relation to get G1. As you can see, some familiar libraries are used, such as NumPy and Pandas. Also, the curve fitting from the scipy.optimize package is used. On the bottom left, you can see the code gets time, intensity, and G2 values from the raw experimental ASC file from the software for the ALV. And then using a for loop, G1 is calculated with the help of a np.polyfit function. On the top left is what a raw ASC file looks like, so there's not much useful information here besides time, G2, and intensity. And then on the top right is an output CSV file from the Python code. And as you can see, it has all of our useful information such as G1, MSD, L star, and radius. The bottom panel shows an example of an experiment I ran recently. On the left is an MSD plot. The curves look fairly linear, although when I scale MSD by time on the right, you see the slope is negative and the sample is actually showing subdiffusive behavior. Therefore, the radius cannot be accurately reported using the current code. So I hope you all see how this mathematical model is very important in accurately extracting information used to analyze rate of emulsion destabilization.